for each expression, each proposition, we define a kind of a function. Okay, we assign something to that proposition that can be true or false, and then we just working to see if so there were some obvious ones, some basic one. Then we put them together to get a kind of a combination or compound. So these are going to be the operation that we're going to use: negation, or connection, and connection. That was a conditional one, and that's a biconditional. So we work on this type of expressions, how we're going to read this new language. Okay, translating from the symbolic one into the word form, and etc. And the other things that we did, the important part is when we combine these propositions together, you have to identify what would happen to the result. Is the result going to be true or false? So we give you a table that you have to memorize it and use this table to identify whether the expression is going to be true or is going to be false. There are going to be all theorems in future. Okay, so then we end up with this expression that when we have a compound proposition, sometimes we get a compound proposition which is always true, regardless of whatever happened to the parts or the atomic one. If it's going to be always true, we are going to call it a tautology. If it's going to be always false, we are going to call it a contradiction. So the contradiction is going to be the statement that's always false. But you may get a statement that it may be sometimes true, sometimes false, depends on the conditions that we have. So that's the one we call it contingency. Okay, so this is going to be your first job. Some of these expressions would be given to you. Then you've been asked, which one is it? Is it a contradiction, contingency, or a tautology? You have to draw a table for us. Okay, you have to draw a table and you identify the truths, values, if you like, of that expression. And for example, this one arrived at a false, false all the time. So that was a contradiction, or the second one was a contingency, and etc. So now we are going to continue. Any question? I posted your practice quiz number 1. So the quiz would cover section, chapter 1, 2 sections. I think it's a 1, 2, 1, 3. And then chapter 2, 2, 1, 2, 2. And the assignments from all these sections would be connected, okay, on the day of the quiz. I will put a place on the canvas. So when you're done with your assignment, you make a PDF file and you submit it over there, okay? Let's see how far we can go. We try to finish this section 2.2, very interesting section. So what is going to be 2.2? As I give you the indication the other day, we would like to compare these expressions together, these propositions, okay? We'd like to make something like when they are going to be like each other, when they are going to be equal, okay? As you know now, each expression would be identified by its truth values, whether it's going to be true or false. So if you want to compare two statements, so you have to compare the truth tables, if you like. If the truth tables are going to be the same, we can say that they are the same. But the expression that we use is logical equivalence. Okay, so that's the argument of this section. So what is, okay, logical? What's going to be logical equivalence? We're not going to have a kind of equality, but it's the same thing. What is going to be logical equivalences? Now, two compound proposition. Okay, two compounds to a statement that would be given to you. Two compound propositions. Two compound propositions, let's say P and Q. Remember the compound one, we use the uppercase letters, are said to be equivalent, like each other, the same. Said to be is said to be logically Okay, it's going to be logically equivalent. Equivalent if they have the same truth table. Okay, if for both of them, okay, if their truth tables are going to be the same, are the same. So they should have the same truth tables. Then they are going to be kind of identical. Okay, so in this case, what we are going to do, the notation that we're going to use, and note that if they are going to be the same, in this case, note that in this case, the biconditional implication, remember, if and only if, the biconditional implications, biconditional implications, P, if and only if Q, this is going to be a tautology because they have the same, they have the same truth tables. Okay, so this is going to be is a tautology if they are going to have the same, Okay, it's going to be a tautology. And we use this expression and we write, okay, so we can write P if and only, but we have to use the two lines here. And only if Q. You can use this one, or you can use a kind of equality sign, P equivalent to the Q. Okay, so if you use just a single line, means this is just a, biconditional implication, or this means P if and only if Q only. But if they are going to be equivalent, this statement is always true. When the statement is always true, it's going to be a tautology, and we use the double line here. So the double line means they are equivalent to each other. Okay, any question? So you got to be careful when you write, we use these two notations. This is just a general one, P if and only if Q. But when you use the double line here, this means they do have the same, okay, truth tables, and also, so therefore it's going to be always true. Okay, question? So we give you some to check for us. Okay, this would be one problem on the quiz. Example, we wanted to show that, okay, show that the following, show that the following propositions, if you like, the following are going to be logically equivalent. Okay, equivalent. So there are famous identities that we can use it all, in future. Especially this first one is such an important one. You better keep a note of this, and we are going to use it. If you want to prove any theorem, you have to use this one. It's so useful. So that's why I'm going to prove it. So if we ask you directly to prove, you have to prove it. Otherwise, you can use it anytime you like. Okay, so this is a very special one. This is, remember, if P then Q, it is the same as equivalent of not P, okay, not P or Q. Very popular expressions. Okay, so you can use this one. I'm going to rewrite it as a theorem in a minute. But if you've been asked to prove it, you have to do it. Otherwise, you can replace it right away, not P or Q. Okay, so how are we going to prove it? You draw the table. Okay, the table for the expression to the right and to the left. If they are the same, you're done. Okay, you can use one table or just do two. So I'm going to do two tables. So I'm going to find what is going to be the true tables of this one. you know that you are going to have, okay, this is going to be your table. So you have the P, you have the Q, and over here, you want to know what's what happened to the if P, then Q. Implication, we talk about it. The case one is true, true. So this would be true. The case two is true, false, true, false. Remember, if you start with the true, this means you have to do it, but you didn't do it. So this would be false. Okay, the other case is false, true. If you start with a false statement, means P didn't happen. So you can do whatever you like. Okay, so if you start with a false statement, this result is always true. Okay, and the last case can be false, false. Again, since you start with the false statement, you don't have to do anything. So this means if P, then Q is going to be true. Any question? It's the one that we talk about it. This is true all the time, except when you start with a true statement and you end up with a false. So get the other one. So that's going to be not P or Q. Draw the table, just use the same, okay, same order if you like, to just show that they are the same. So this is the P. Okay, this is going to be Q. You need a not P. So you form the not P, and you end up with a not P or Q. Okay, same, they use the same order from the right so that you show that they are the same. So the first part is true, true. So this would be false. Not P or Q, since Q is, it's going to be true because one of them is true. Okay, so the Q is true, so this is going to be true. Next case, true, false. P is true, Q is false. Okay, so the not P would be false. So the not P is false and the Q is false, so the result is going to be false. Okay, the next one, false, true, false, true. So the not P would be true. So we get a true, true, which is going to be true. And the last one is false, 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 false. So the not P would be true. So one of them is true, the result would be true. So you see, if you compare them together, this is the truth values of the first one, and this is the truth values of the second one. As you can see, both of them are the same. So if P then Q is the same as not P or Q. For some problems in future, that give you a very nice shortcut. So you have to be careful. Any question? So this is how you take care of this statement for us. And so this is one that you can memorize it. You can use it anytime you like, but make sure you know the proof. I'm going to give you another very popular one that we can use it anytime we like. Okay, are you done? This next one is going to be introduced later on. A very famous one. Okay, number 2. You see that's the one. If P then Q is equivalent with not Q implies not P. This is going to be called contrapositive property, later on. So we just prove it over here so that you are going to use it in future. Okay. Again, you can, get 2 tables. I'm going to do both of them in 1 table so that you know that if you do it on the test, we accept it. So the solution is going to be, I'll go with this part first. Okay, so draw a table. So you are going to pick the P, then you need the Q. Okay, so then you go with the P, then Q. That's the first part. Provide the second part. For the second part, you need a not Q. So that's going to be not Q. Then you need a not P, not P. And the result that you are interested in is not Q implies not P. See, that's another way to write it down. Or, you know, whatever you feel more comfortable. Two table or just a single table. Okay, are you ready? There you are. True, true. This is going to be true. Not Q would be false. Not P would be false. You have the implication. Remember, if you start with the false statement, this is always true. Okay, we talk about the conditional. Implication is true if the starting one is false. Next, true, false. True, false. This is the implication. You start with the true statement, but you end up with the false. So this would be false. Okay, it would be false. Now, not Q is going to be true. And the not P would be false. The same thing over here. You start with the true statement, you end up with the false. So this would be false. Question? Just continue. Next, false, true. Since you start with the false statement, this is always true. Not Q. Not Q would be false. Not P would be true. The same thing. You start with the false statement, so the implication is true. Okay, and the last one, false, false. So we start with the false statement. This result is always true. Not Q would be true. And the not P would be true. True, true, the result would be true. That's it. So as you can see, the truth values of this statement and the other one, both of them are the same. So this means, yes, they are logically equivalent. So if P then Q is the same as a not Q implies not P. And then we're done. We call it contrapositive properties, you know, later on to get these numbers. Okay, question. Now, there are some famous one. Famous identity, we are going to list it and you can use it anytime you like. Okay, so as a theorem, it's a very big theorem over here. You see this connective or and you apply it to two propositions. So this type of operation is called binary operations because you need two to handle it. With the numbers, addition, subtraction, multiplication is binary operations because you pick two numbers, you add them together. You pick two numbers, you multiply them together. So addition and subtraction would have some properties like commutative, associative, distributive. So it's going to be the same thing for this type of idea of the propositions. So this is going to be, we call them logical identities. Okay, that's it, radical identities. And some of them are obvious, a couple of them are important, so I'm going to give you the hint which are going to be more important. So suppose you start with some atomic proposition. Suppose we have the P, we have the Q, we have the R, etc. Are given propositions, are given propositions. Okay, then the following are true. Okay, then the first one. You see the first one is P or Q. We can switch it, commutative property. Is the same as Q or P. So if you switch it, the numbers are going to be the same. It's like addition, if you like. And it would happen for the other one too. P and Q is the same as Q and P. Okay, that's one. When you have these binary systems, if you like, in logic or in general in mathematics, you see, if you have one of them in terms of the first connective, which is the OR, if you change these ORs into the AND, you get a similar result for the second one. These type of expressions, if you change it in logic, we say this second one is a dual of the first one. Okay, so if a theorem is true, then the dual of that theorem is also, that result is also true. We call them duality, properties, but it's not a big deal. You can list it, but not bad to see this type of expressions. Okay, so this is, if you like, a commutative property. Okay, we call it property C, if you like. This is going to be commutative property, if you like. So it's like a number, like the set in future. Okay, so that's going to be the first property. Any question? You can have something like associative property. You see, associative property for multiplication or addition. So if you have three numbers and if you want to add them together, for example, you add them two at the time. So if you have the P or Q or R. Okay, so this is going to be, you can switch these parentheses. So it's going to be the same as P or Q, then or R. Okay, so the order is not important. You can pick the first two and they get the third one, or you can do it the other way around. And it also be true if you just change these connectives. It's going to be P and Q and R. It's the same thing. It's going to be P and Q and R. Okay, you know that this type of property, we refer to it as what? Associative property. Okay, associative property for the number or or otherwise. And they are clear. If you want to prove it, you have to draw the table to get these numbers down. So commutative, associative. The third one is distributive. This is a little bit different. You know that if you want to multiply something like 2 times x plus y, would be 2x plus 2y. We just distribute it. It's the same thing over here. So for example, if you want to find the P and Q or R, it's like A times B plus C, if you like. You can distribute it. It's going to be A times B plus A times C. So it's the same thing here. It's going to be equivalent to, it's going to be P and Q. P and Q, you see, like multiplying. Then we get this sign, or P and R. See, it's like a distribution that we have for the numbers. Okay, then the dual means if you switch these. So if it's going to be P or Q and R, it's going to be the same as, the P or Q and, okay, P or Q and P or R. When you compare it with the numbers, you don't have this one over here. So this was something like A plus BC. A plus BC is not A plus B times A plus C. You see, this is only the difference are going to be the one. So you cannot have this one all the time. In your field, you have something that you call it the Boolean algebras. So the Boolean algebras are going to be the system that you have these binary operations. You can replace it by anything you like, addition, subtraction. So the Boolean algebra is going to be a system with these binary operations that always satisfy the distributive law. You have some systems in computer science that they are not satisfying this part. Okay, so this is going to be a key argument. So the expression is going to be, this is distributive. Okay, distributive property. So if you have a distributive property in your field, you are going to call it a Boolean, okay, Boolean algebra. And that would behave, would have a very important part in your fields. We used to teach it in discrete mathematics, but they said that you have a couple of other courses that they talk about the Boolean algebra from the computer science point of view. So that's why we don't cover it. Okay, any question? Now we get to the one that you have to use. You see, look at this one. These are going to be used, or you can use it anytime you like. The first one is, remember the negation of a, okay, we call it the double negation property. What does it mean? This means the negation of the P is the same as the P. Okay, it's double negation. It's like, opposite of the -5 is 5. Okay, it's something similar. So it's going to be the negation of the P is P. It would be very useful, and we are going to use it. Okay, so that's the first one. Next one. This is very important, okay? The negation of P, okay, the negation of P or Q is equivalent to, is going to be equivalent to the negation of the P and, okay, negation of the P and the negation of the Q. So that's going to be the one. We distribute the negation, but you have to switch. You switch from or into the, okay, e to the n. So the dual of this is going to be the negation of P and Q. Is going to be the same as the negation of the P or the negation of Q. Very useful. You get a couple of problems from this one. We give you one at least on the quiz, of course. This is called the De Morgan law. You must know them by name. Okay, De Morgan. This is going to be, that is De Morgan's law or laws. De Morgan is, it's a French mathematician, if you like. He has done quite a lot. He just gave you the foundation of the probability that that you use. So it's quite something, his formulas. And there are some other, he got some very strong works in mathematics and probability. So you have to know this one. You refer it by name, De Morgan law. So basically, if you want to find the negation of or combination, you change it to the and combination of the negation. And if you want to find the negation of the and, it's going to be negation of the P or the negation of the Q. And there is going to be a kind of a set theory version. In that case, instead of the negation, use the complement. So we get to the chapter 6, and then we repeat this one for the tests. Okay, any question? Again, if you want to prove it, you have to draw the table to get this done. So in some of your problems, they may ask you to prove it, but we accept it. Now, the next one, very important again, number 6. This is the one that I did prove it for you. If P then Q is the same as not Q implies not P. Okay, the name for this one is, we call it contrapositive. Contrapositive. Contrapositive property or law. So when we want to use it, we say, by contrapositive law, if P then Q is the same as not Q implies not P. It would be, we use it, when you want to prove something. In mathematics, sometimes to prove the negative version of the theorem is much easier to prove this one. You say that's going to be the one. For example, if you want to prove that this is using calculus, we know that we can prove that if a function is differentiable, then the function is continuous. So this version would be, if the function is not continuous, the function is not differentiable, which is much, much easier to handle. We know that if the function is not continuous, there is a break, there is a gap. And you know that if there is a gap, you cannot have a tangent line to the graph of the function. And if you cannot have a tangent line to the graph of the function, your function is not differentiable. So automatically we get it. So sometimes it would be useful for us to use this equivalent form rather than the first one. And you are going to see it in chapter 5 when we talk about method of proofs. Okay, so get to know it. It's a very popular case. That's number 6. And number 7. Number 7, again, this is the one that I proved for you. Remember, that's the one. If P then Q is equivalent to not P or Q. It's the one that I proved. Okay. If P then Q is equivalent to the not P or Q. Very useful again when you want to prove theorems. Now, question. The way you are going to use this one in several places in this course, and if you miss it, you miss these points in all the tests and the exams that we're going to have, is that we are very much interested in the negation of this one. Okay, what is the negation of if P then Q? You see, so you better make a record and keep it. So what's going to be the negation of? The negation of if P then Q equivalent to what? Okay, this format is going to be very important for us. Any suggestion? You see, if you want the negation of the term to the left, you have to find the negation to the right. To find the negation to the right, you can use the De Morgan law. So it's going to be the negation of the first one and the negation of the second one. So what's the negation of the first one? What's the negation of the P?
P.
P. Very good. P. And since we use the negation, we change this one into and the negation of the Q. Such a useful expression for us. Such a useful expression. You see, sometimes a theorem would give you, they give you a theorem and you want to prove it, you say, oh, suppose not. Suppose not. What does it mean? Suppose not means suppose we have P and not Q. Means, we have the P, but not the Q. And you will see we are going to use it quite a lot in this course. And nicely it can be done. You use this type of idea indirectly in calculus. Okay, use it in calculus, but you didn't, refer it to it. I'll give you, when we get to the notion, various format. Okay, so make a note of these very tricky expressions that we're going to have. You can use it anytime you like, as I told you, unless, we ask you to directly to prove it. So if you want to prove it, that's it. So you just make a table to the right and to the left to get these numbers. Okay, any question? There are some more. Okay, question?
What is number 7 called?
We don't have any special name for this one. It's just implication equivalent, if you like.
Okay.
Okay, equivalent. And this is just a negation. This we refer to as a negation of the conditional implication. Okay, just make a note. The negation of the, I can write it down, just the negation of a conditional expressions. And you will see when we get to the other chapters, we use it quite a lot. So that's a red flag, if you like. Make sure you know it, and I'm going to give you an example in a minute. There are some others, okay? We are not going to use it, but just for your information, I just write the 8-1. This is a kind of, if you do the operation with the multiplication, the usual one, you can have powers, for example, you see. You have a times a would be a squared, this type of ideas, if you like. But for the implication, we have something like this is it, p or p. Okay, it's the same as the p. That's going to be the one. You know, you don't have something like this one in addition. But we are going to talk about set theory, we get it. Okay, but if you change it to the dual, is going to be, this is the one, p and p would be p. So this is like a p squared. If you don't have the p squared in logic, but it's like the p squared. So you get a p squared, you get back to the p. So then you can define the powers if you like, you know, p cubed would be p, p, p. So again, that gave you back to the p. In linear algebra, if you have this type of, if you have done it, or, you know, in general, if you have the p squared, which is going to be equal to the p, we are going to call the p a projection over there, or idempotent. Okay, so just want to see this name in your book. They don't use the projection, so this is going to be idempotent law. So this means you are not going to go with any power, if you like, to get these numbers. And it's not going to be used over here. But the one that I circle, we use all of them. So you should expect somehow these in your quiz, or at least one of them, to give you these numbers. Okay, any question?
For all negations, are we going to flip the and ors? The and
Yes.
to ors? Okay.
Yeah. That's the rule of the Morgan law. Yeah, all the time. Yes, that's going to be the one. Now let's see how we're going to use it. We give you an expression and we ask you to give us the negation of that expression. Okay, so be ready for it. I have quite a lot of your assignments are related to this concept. You have, I think, one question on the practice quiz, then I'm going to check it right away. This is your job. Example. We wanted to find the negation of each expression. You see, find the negation. Find the negation of each statement or proposition. Negation of each statement. Okay, we go with the first one. What is the first one? It may be something in word form or just symbolic form. First one is this one, John. Okay, John is a math major. John is a math major. Okay, major, and John's brother. Okay, John Brothers is a computer science major. Computer, okay, science major. Science major. That's it. We want to find the negation of this statement. The way we do it, you change it to the symbolic form and then operate. Most of the time you have to use the De Morgan law. So this is the way we like it. We are going to make it into symbolic form. So what do you need? John is a math major, you call this one P. Okay. John's brother is a computer science major, you call it Q. So what do you have? You have P and Q. Okay, so what you would like? So the solution is going to be, you would like to find the negation of P and Q. So this is the question. Okay, any question? You better be patient and nicely change it to the symbolic form, then you go for it. Now, you know what does it mean, this one? Remember De Morgan law?
Not P or not Q.
That's it. So you remind yourself that with the De Morgan's law, if you like, we know that the negation of the P and Q is the same as the negation of the P or the negation of the Q. Okay, now give us a translation in word form. Tell us what does it mean, or what is the negation? We know that the negation of the P and Q is a negation of P or negation of the Q. You want to try?
John is not a math major, or John's brother is not a computer science major.
Excellent, that's it. Okay, so you have to write it down for us. You know, this is the way I suggest to change it and then do it. Or sometimes if you feel very much comfortable to give us right away, we accept it, but you better check it. Okay, so John is, yes, John is not a math major. Okay, major or okay, John's brother. John's brother, okay, is not a CS, you know, student says a computer science. Computer science major. Okay, so this is the way we are going to use those theorems that we talk about it. Any question? So change to the symbolic form, apply the result, you say whatever you know, then you come back and rewrite the statement, give us the result. Okay, that's the first one. And you have a list of these type of problems in your assignment. So I just want to make sure you know what's going on. So check the, ready for the second one? The second one is this one. Okay, the unit digit, or the unit digit, whatever, digit of this number, 4 to the 67. 4 to the 67 is 4, okay, is 4 or it is 6. Okay, so you know when you raise it, then you get the unit digits. This is going to be either 4 or is going to be 6. Okay, then you have to change it to the symbolic form again. So the unit digit is going to be 4. You are going to pick this one to be P. The unit digit is going to be 6. We call it Q. But you see, you have the or in between. And so what you are looking for, you are looking to for the negation of the P or Q. So that's going to be the one. Again, you know that, right? De Morgan law, you change it. That's it. De Morgan law. So the negation of the P or Q would be equivalent to the negation of the P and the negation of the Q. Okay, so that's going to be the one. Okay. You want to give us the answer? This is your statement, and tell us what is the negation of the P and the negation of the Q. Let's try.
The unit digit of 4 to the 67 is not 4 and it is not 6.
That's it. Yes, the units digit of, okay, unit digits of it of 4 to the 67. Not P is not 4, and the other one, not Q, is not 6. is not, okay, it's not 6. Not 6. That's the way you know that. The way you write it down. There's some other way to do it, some other expressions. There's not bad to know it, that this is one version. The other version is that you may use, you may say that the units digit of 4 to the, okay, 67 is, okay, is neither or neither, is neither 4 nor 6, which is the same thing. Okay, so this first one is safe, and you read it as is to get to get these numbers. Any question? So change it to the symbolic form and just give us the answer. That was number 2. The popular one is the next one from algebra. Are you ready? And you have at least one of, I think, question number 6 on that practice one that we have are covering this concept. And maybe we give you some of them. We want to find the negation of this one. You see this inequality. -10 is less than x and it's less than equal to 2. It's very popular from algebra. You see, algebraically, but we want to do it logically, just using this idea. What is this? If you put it on number line, is the number between -10 and 2. This is a -2, a -10. You don't have it, a -10. And this is going to be 2. So this means this portion. Okay. So if you want to find the negation means anything outside. You see, this is going to be whatever you have. The negation would be the leftover. So what is going to be the leftover? You see, you get this one over here. You have a -10, but you have to fill it up because you don't have it here. You get it here. And the 2 was solid. Then you have to make a hole here. Now the complement, if you like, the negation would be anything outside. So the anything outside means you are here or you are going to be here. So if you are here, this means x is less than equal to the -10, or because there is a gap, or x is greater than 2. You see, that's algebra. Okay, but you have to give us, explain it in terms of the propositions. Okay, so that give you an idea. But the proposition part is, what is this equation? Remember, we call this one 3-part inequality in algebra. So this means x is greater than -10 and x is less than equal to 2. So if you want to do it using the logical format, you pick the proposition P to be the fact that the x is, x is greater than -10. So this is going to be your proposition P. And then you pick the proposition Q to be what? To be the fact that the x is less than equal to 2. You see? So what you are going to be interested in, you are interested in the negation of the P and Q. You see, this is what you want. Okay, x between -10 and less than equal to 2. Now we know that by the De Morgan law. So again, by the, just switch to the De Morgan law. Again, law. So what is that? The negation of the P and Q is going to be the same as the negation of the P, or the negation of the Q. This is going to be the case that you're going to have. Now you translate it to the, to the algebraic form, if you like. So the final answer would be of this form. You would like to find the negation of the -10 less than x less than equal to 2. So this would be the same as the negation of the P. This is the P. So the negation is you switch the sign of the inequality, x greater than. So it's going to be x less than. So this is going to be the first part is going to be x less than equal to -10. Okay, less than equal to -10, or you can say or just write on a symbolic form, or the negation of the second one, x less than equal to 2 would be x greater than 2, which is exactly what we got over here. Okay, so if you want to write it down nicely, this is it. The negation of the -10 less than x less than 2 is equivalent to, you negate this one, x less than equal to the -10. That is the first part, or x greater than 2. So that's the best version to write this one in symbolic form. Very popular case, okay, for the combination of algebra and how we translate using our language. Any question? So when it's on the test, this is how we're going to do it for us, okay? You have to explain it. You have to explain how you get it, okay? Don't write just the final answer. Just tell us what did you use to get this one, especially that Demogorgon one. Okay, any question? Be aware of this equality sign. You know that when you negate, you you reverse the sign of the inequality. But over here, you have a strict inequality, if you like. But when you change it, you are going to have an equality sign here. And the second part, you do have the equality sign is already given to you, then you have to switch it to get these numbers done. Okay, any question? So you will see one, you have one in your practice quiz, and you should check that one. You already got the solution. I post the solution for that one, that quiz. That practice one used to have 8 questions. Those last 2 questions are from section 2.3 that we are not going to cover. So when you read that practice solutions, okay, to that practice quiz, ignore the last 2 problems. Okay, that's one. You will see it when we get to the test. So, I just post it quickly so that you can have it. Later on, I can modify it, drop that too. Okay, so this is going to be number 3. Any question? No. We need one more. And this one is a tricky one. This is the one that on the test, most of you are going to miss it. Okay, just give it a warning. Let's see, what's this one? That's interesting. That's that conditional one that I told you. The negation of the conditional. Okay, that's one. You can find the practice quiz, everything on the canvas. That's one. Okay, so this is the one I talk about it. If P then Q, you want to negate this one. Okay, so what is this? If if I pass math, 245, then I graduate. Okay, then I graduate. You want to find the negation of this one to get the numbers, okay? So as you can see, this is the implication, is a conditional implication. And so you have to translate it first, okay? So what we do, we are going to call this one P. If you pass the math 245, you graduate, you call it Q. So that would be useful, to be patient and change it first. So this is what you need to find. The given one is if P then Q. So what you are interested in, you are interested in negation of the P, if P then Q. You see, this is what you are interested in. So you must know that formula that I gave you. That, remember, note that. Note that the negation of if P then Q remember, is the equivalent to the P but not Q. See, that's formula that you have. The negation of if P then Q is going to be P but not Q. P and not Q, or P but not Q. Okay, that's going to be the one. Any question? Now give us this expression from the given one. Anybody wants to read it? Because you are not done, remember, this is just a symbolic one, and you have to go back and transcribe it or translate it if you like. Any suggestion? P and not Q. Yes, go ahead.
I passed math 245 and I do not graduate.
That's it. Yes, that's it. Very good. I passed math 245, but I don't graduate, or I didn't graduate. It's something like that. Okay, it's a P and not Q. P and not Q. And the important part is it's not going to be a conditional implication. Most of the people, the way they do it, this is it. I get this on the test. They say, if I don't pass math 245, then I don't graduate, which is wrong. It's not the negation of these expressions, okay? So we've got to be careful, because the negation is going to be this one. So there is not going to be implication. So this is it. The P, I pass. Okay, I pass math 245. Okay, you can say and not Q, and I, okay, don't graduate. Don't, graduate. This is one version. The other version is, you see, some people like this one. Some people like the fact that I pass. That's better. Math 245. Okay, but I don't graduate. Okay, I don't graduate. That's a nice one. Okay, so just make sure that don't miss it. And this is very popular, the negation of this implication. It's popular now, and when we get to the proofs of the theorems, we're going to use it. So just follow the rules, okay? Follow the rules. So if you just use the common version, everyday life, you miss it right away, okay? Follow the rules. It's especially for the conditional implications. The negation of the the negation of the if P then Q would be P but not Q. P but not Q. Then you translate it. P, I pass math 245, but I don't graduate. Okay, so that gives you the one. Just make sure you don't miss this one. As you can see, they are very, very popular, and you are going to use all of them. So one question of that 6 questions that are going to be given to you on the quiz is of this version. We make up something, we give you a couple of statements, and then you are going to do it for us. And you get quite a lot in your book. No, this is not contrapositive law. No. You mean this one? No. Contrapositive is if P then Q is equivalent to the not Q then not P. It's something quite different. Okay, the contrapositive one. You just want to find the negations. Okay, so this is the 7th one that I tell you. Okay, we have one more to go, and that gives you a very nice question. Now, when we talk about the theorem in mathematics, again, I bring a theorem from calculus, which is easy to understand. So the theorems would be given to in the form of implication. You see, if P then Q. That's one. If P then Q. If the function is continuous, then the function is integrable. So that's going to be if P then Q. Then sometimes a theorem would be given to you, say, oh, the converse of the theorem is also true. Or sometimes we say the converse of the theorem is not true. So In this type of expressions, we are going to use, the given theorem, the converse, and there are some other expressions that we're going to use. And sometimes these expressions can be confusing. So we are going to introduce, if a statement of a theorem is given to you, you should be able these following format for us. There are three formats. What is the contrapositive of a given statement? What is the converse of the statement? And what's the inverse of an expression? Okay, so that will be the last topic in 2.2, and you can get a kind of two sets of problems in your assignment for this one, and we give you one. Okay, so what is contrapositive or contraposition? I just go with the contrapositive. What is contrapositives of the given expressions? What is converses? Converses. And what is the inverses? Inverse. Okay, inverses. And they are popular, we are going to use it in various places when you're dealing with, programmer, etc. Okay, I'm going to explain each one of them, then we give example, that's it. First, introduction of the contrapositive. You see the contrapositive or contraposition. The contrapositive of these implications of if P then Q is not Q implies not P. That's it. That's the first one. So if you give you a statement and ask you what is the contrapositive of that statement, you write it down first, then you translate it for us. Okay. So the contrapositive of if P then Q is going to be not Q implies not P. You know that they are the same for the contrapositive because we have the contrapositive law for this one. Okay, that's the contrapositive. Any question? Getting the second one of these expressions. What is the converse? If you switch P and the Q, you get the converse. So that was the contrapositive. So what is the converse? The converse of if P then Q is if Q then P. Okay, if Q then P. So you switch the P and the key to get the Q to get the converse. Okay, that's the way we do it, in mathematics. So it's very easy for you to write it down. You just switch it and you read it. Okay, so that was the converse. Now what's going to be the inverse? This is the one that most of the people be confused and they missed it. Okay, even when you deal with the proof of the theorem. So what's the inverse? Okay, the inverse of if P then Q is going to be not P implies not Q. See, that's the inverse. The inverse of if P then Q. Okay, it's going to be if P then Q is going to be not P implies the not Q. Okay, that's going to be the inverse. The only relation that they are going to have with each other is this one. You see, note that we talked about this one before. If P, we proved it, in fact. Contrapositive law. If P then Q is equivalent to the not Q implies not P. So this means any statement and its contrapositive are the same, are logically equivalent. So this is the one that we already talked about it. So I just repeat it over here again. And this is that's going to be the contrapositive property. Contrapositive law. You don't have any other relationship between these three expressions. Okay, so we give you one statement and we ask you to find this for us. Contrapositive, converse, and the inverse. So you can write the formula for yourself first and then translate it, and then you're done. Okay, are you ready? Then we're done with this section 2.2. So what's the example? The example is, we would like you to write. Okay, write the contrapositive. Contrapositive. Contrapositive converse. Converse and the inverse. And the inverse. Inverse of each statement, of the statement. Of the statement. So this is the statement. If n, a number. If n, okay, ends, if n ends in a digit 2, in a digit 2, then n is divisible. Divisible by 2. That's the statement that we have. Okay, if n ends in a digit 2, then n is divisible by 2. Is it true or false? This is a statement. If a number ends up with 2, then the number is divisible by 2.
It's true.
It's true.
True.
It's true because you end up with a 2, then it's even number. When it's end up with a 2, it's even number, so it's divisible by 2. So the statement is true. But they ask for these 3, so the way you are going to do it, you have to change it to the symbolic form that we have. You see, n ends up with the digit 2, you are going to call it p. N is divisible by 2, you are going to call it q. Okay, so there you are. So you have a p, if p, then q. So this is given to you. So give us those terms that we talk about it, okay? So the first one, the contrapositive. It's not bad to repeat it and then write it down. Even if you write it, we accept it. You know that I just repeat the contrapositive. You don't have to for the test. The contrapositive of if P then Q, you know that is not Q implies not P. Write it down first, then translate it. Okay, any suggestion? Give us not Q implies not P. And this is if P then Q.
N is not divisible by 2, but sorry, if n is not divisible by 2, implies n does not end in digit 2.
That's it. Yes, so this is going to be one. See, not Q would be if. You have to use the if because it's a conditional. Okay, if n is not divisible by 2, that's the first expression, then, okay, then, now the negation of this one, n ends, okay, in the digit 2 would be n does not end, then n, okay, does not end in a digit 2. A digit 2, and then we're done. Any question? So just check the formula for yourself first. Okay, the contrapositive of if P then Q would be not Q implies not P. So you read it. You have to start with the if because it's a conditional one. If the negation of the Q if the negation of the q would be n is not divisible by 2. So if n is not divisible, if n is not divisible by 2, then n does not end in a digit 2. Okay, that's a contrapositive. Any question? Go for the second one. What do you want? Converse. That's easy. You switch. Again, I like to remind myself and write it down. You don't have to. You remind yourself that the converse of if P then Q, okay, the converse is going to be is we switch. If Q then P, that's it. That's a converse. Okay, so what is this one now?
If n is divisible by 2, then n ends in a digit 2.
Very good. Yes, if Q, this is it, if n is divisible, okay, divisible by 2, yes, then n ends in a digit 2. Okay, digit 2. That is the converse. Any question? No, we have the inverse. Now what's going to be the inverse? The inverse, just to remind myself again, that the inverse of if P then Q, okay, inverse of the if P then Q is, remember the inverse is not P implies not Q. That's the inverse. Not P implies not Q. Okay, so what is this one now? I'm sorry, not P implies not Q. I missed this one. It's a Q.
If n does not end in a digit 2, then n is not divisible by 2.
That's it, yes. If, okay, negation of the P, if n does not. Okay, this is it, does not. And, okay, in digit 2, then n, okay, n is not divisible by 2. Divisible by 2. Is it true or false? If a number is not end up with the 2, is it follow that that number is not divisible by 2? Is it true or false?
False.
It's false, you know that. It's going to be false because what number can end up with a 6 is an even number is divisible by 2. So as you can see, the expression was true, but the inverse was false. So that's, that would happen from time to time. This is 2.2 to get the numbers. Okay, just make sure that be patient to write it down. This section is very important. 2.2. So get 2 or 3 problems from this one. Then for the quiz, you see some of them are. We are going to give you must know what is going to be tautology. Okay, what's that? Contradiction, tautology, the same thing that that I did. But sometimes you should be able to read some of the problems, and you have a couple of questions on the functions. Okay, so we give usually one question on the functions, and I can quickly take care of maybe I'd have time to just do 1 or 2 for you. But read the practice one, read the solution. If you have any question, you can email me if you like. I just want to be set on time. Just give you that quiz. That's the one. But don't worry if you have any question at the beginning of the lecture. Again, I can work on that. Okay, so just let me know. We give you one question on the functions. Okay, it's not going to be a big deal. just the definition of a function. So that's a practice quiz. Okay, practice quiz number 1. The first question on function. So we are going to make something up for you. This is going to be the set A is given to you. The set A got a -2, 0, and 2. And then you have the set B, which is a 4, 6, and 8. Okay. And then we define a kind of a function or a relation. Okay, in this case. And we defined a relation R from A to B by this definition. Okay, remember the definition is that because the relation is going to be just a connection of order pairs. So this is it. The definition is that X and the Y is A cross B. They are going to be related to each other. Okay, so X is related to Y if and only if X minus Y is going to be divisible by 4. If you divide it by 4, the result is an integer. Okay, so this means if you want to collect your members in your relation, your members must satisfy this condition. So what we'd like to do is we'd like you to list the members. List all the members of the R, okay? List all the members of R as order pairs, if you like. And then we may ask some question, whether it is a function or just, we just compare them together. So what you are going to do, you have to find the A cross B first, because this is the total number that you're going to have. Remember A cross B, you get 3 elements, and the 3 elements here, 3 times 3 would be 9. So you have to identify those first, okay? So the solution is going to be, so you pick A, so you just remind yourself that, note that your A cross B, okay, your A cross B has 9 elements. 9 elements. You have to list all of them. We talk about how to list them. It's going to be A cross B equal to order pairs. We're going to match each members of the A to the B. So -2, 4, -2, 6, -2, 8. So that's going to be -2, 4, -2, 6, -2, 8. So you come back, you pick the 0. So it's going to be 0, 4, 0, 6, and what? 0, 8. 0, 8. Then you're going to pick the 2. So it's going to be 2, 4. Okay, 2, 4, 2, 6, and the 2, 8. 2, 8. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have these 8 numbers. Okay, this is 2, 6, and the last one is 2, 8. Now you have to check to see which of these are going to be in your R. The condition is the difference between X and the Y must be divisible by 4. So you can test each one of them quickly, or just test a couple of them and just give us all the members, okay, to see if it's going to be the case. So for example, if we get -2 and 4, you see the difference would be -6. -6 is not divisible by 4. So you drop it and just check this one. You see, you check the -2 and 4. So this means X is equal to -2. Y is equal to 4. So X minus Y over 4 would be, X is a -2 minus 4 over 4. So that gives -6 over 4. You simplify that, giving -3/2. So it's not an integer. Okay. So this is not an integer. So this means -2 and 4 is not or does not belongs to R. Okay, and you quickly check the other ones to see if it's going to be the case. You see the negative, the next one is -2 and 6. You see the difference is going to be, the difference is a -8, which is divisible by 4. So -2 and 6 is a good one. So this belongs to R. Okay, because -2 minus 6 over 4 would be -8 over 4, which is a -2. Okay, and you check the other ones right away. The next one is not a good one. -2 minus 8 would be -10. It's not divisible. Okay, this is not in R. Next, 0 and 4 is good. 0, 4, because the difference is 4. 4 is divisible by 4. So that's a good one. 0, 6 is not, because the difference is 6. So it's not. 0, 8 is a good one, because the difference is 8. It is divisible. Okay, 2 and 4 is not, because the difference is 2. Okay, you can list it, we accept it. Let's just explain it. 2, 6. 2, 6 is a good one because the difference is 4. And the last one is 2, 8. It's not a good one because the difference is 6. Okay, so how many members are you going to have? And this is it, 1, 2, 3, 4. So this is R. Okay, so the R is going to be, this is it. We get the -2, 6. Okay, we get the 0, 4. 0, 4, 0, 8. 0, 8, and you get 2 and 6. So this is going to be, okay, your relations. Any question? So we give you one question of this format. And then we may ask you if this is going to be a function. Remember, in order to have the function, you have to have two conditions. The first condition is you must cover the A. A is a -2, 0, 2. -2 is covered, 0 is covered, and the 2 is covered. So the first condition is satisfied. But what is the second condition? The second condition is that you cannot have any shading. You see the first component, 0, 4 and 0, 8. They share the first component. So this means this is not a function. Okay, so R is not a function. It's not a function. And the reason is that 0, 4 and 0, 8 have a common, a common first component. First component or input. Okay, so this is going to be the function question, if you like. But the rest are just translating. Just so read that solution sets, and if you have any question, just let me know. So the assignment, 2 sections from chapter 1, 2 sections from chapter 2. There is another section in chapter 3, quite interesting. And we call it valid statement. We are going to cover that one. Then we are done with the propositional logic. We introduce the systemic mathematical system, and we start proving something. So that's going to be the one. Any question?
Professor, what was the first condition again?
The first condition is you must cover all the members of the A, the domain, remember? -2, 0, and 2. Okay. So you check to make sure that these are present, okay? And then you go to the second condition. So it did satisfy the first condition because we have the 0, negative. So A is covered. Remember, you must cover the A. So A is covered, but the difficulty is they share the first component. So that's going to be there. And that's the one. Okay, any question? So check that the solution one, we don't have any, that's your, yeah, you know that we are not going to have a class on Monday. That's the one. So your quiz is going to be on Wednesday. So you have enough time to practice. And if you have anything, just let me know. Email me if you have any difficulty. You know, sometimes we can arrange a Zoom meeting to explain something for you. Just email me, then we can set up that one. Okay, have a good one and take care. Bye-bye.
All right, thanks.
Thank you, Professor.
Thank you.
Bye.